And the final panel of the day, so we're delighted to welcome Melchiorre Conti, who is going to lead the panel discussion. He is a space resource engineer at ESA. Thank you so much. And we have Bernhard Hufenbach from ESA, Kathyrn Hadler from ESRIC, John Vrublevskis from Thales Alenia in the UK, Space UK. And we have Bertrand Baratte from AirLiquide, but he's representing Euro to Moon, Jerry Sanders from NASA. And joining us online is Jorge Alves from ESA and ISECG. So I'll hand over to you. But he's not online yet. Right. So Jorge is not online yet, but he will be.
So thank you, everyone, for sticking with us. We are the last stint of this very intense, very long, and very interesting conference that now draws to a close with what is the next steps in terms of the pilot plant. You heard the Director of Human and Robotic Exploration talking about it. I mentioned it here and there. Jerry had a mention to it during his talk. So without further ado, I would just jump in, given that we need to compress a bit the schedule. Bernhard, as the lead of innovation and commercialization at ESRIC, could you give us a brief introduction of what is the concept of the lunar pilot plant?
Yeah. First, some context. I must say the topic of space resources is immensely broad. If you listen to the conference, all the different talks, technology, enabling research, processes, application, architectures, it's a huge field. We in ESA have established in 2018 an ESA space resource strategy for the first time. And I think that really shows the intent of Europe to be ambitious and play a role in this field, which is good. But if you listen to the conference, it's a huge area, and hence we need to focus. If we want to play a role in the international context, and I have a strong partner left to me with probably 10 times as much investment as Europe in this field, we need to focus to be meaningful and credible. We also need to communicate clearly to our international partners, to our commercial partner, what is the role of ESA, what are we willing to do in the next 10, 15 years to advance this very topic. And that's why we focus on the pilot plant. Our idea really is that ESA wants to develop and operate in ISRU. I hate ISRU because nobody knows what it is out there in this room. Let's call it the Space Resource Pilot Plant. We want to operate by mid-2030s. We want to deliver it with our own lander. If you listen well to our Director for Human Robotic Exploration, ESA intends to develop a large logistic lander which should become operational by 2030, which gives us autonomous access to the lunar surface. And this very same lander should develop our ISRU space resource pilot plant to the moon by 2035. That gives us a very clear focus. We focus on Regulus for now, get most out of Regulus. And we have, based on this, developed a 15-year research and development roadmap. 15 years, because we want to lead to an application, need to show that the topic of space resources creates value to exploration. I'm sure we can talk to Jerry a lot. He's doing this, I think, as long as he's working for NASA.
Close.
If you don't watch out, this can become a lifelong research and development exercise because it's so exciting. But we want to create value for the space exploration program. We want to show that actually we can do something with the resources. So that's why we want to have a pilot plan and really try to embed the products in an operational architecture for human service operation, which will be defined by NASA, hopefully with some engagement of the international partners. So we want to show what we can do with it as a showcase and as an accelerator for the future. And focusing on this allows us to engage commercial partners, international partners, in order to really add value to the international community. So in order to accelerate the innovation and make progress, our next step is that we develop a ground-based pilot plant, but not in 15 years, but in 2 or 3 years at the latest. And this ground-based pilot plant should be fully representative of the space-based pilot plant. It is meant to become the biggest, most visible space resource facility in Europe. It will happen to be located here at ESRIC. And we want to make it open, an open architecture. We want that this pilot plant is open to international and commercial partners to demonstrate the end-to-end value chain of what we want to do on the moon in 2035. And now it's important. We don't want to develop alone. We will start the requirements formulation phase in the coming weeks, and we will invite the community, international partners, but also academia, private sector, to help us to define the requirements. And our aim is, in the next year, to develop an international interoperability standard for this pilot plant, to really make sure that we have an open architecture where everybody can come, plug and play with this tool, and demonstrate the value of your innovation in the end-to-end value chain. Mel's objective for next year will be to develop this interoperability standard. We will make it open, public, and the aim is that next year, at this event in 23, we will present the first version of the standard and start the development of a pilot plant as a community activity, and together with our new director of ESRIC.
Yeah. So I have my job already lined up for next year. Jerry, Bernhard gave us a lot of good talking points. I guess what I want to ask you is, what does this European initiative represents for future collaborations internationally, with NASA in particular, in the medium, but especially in the long term? We chatted about this, so...
Yeah, I was going to say, actually, I'll just take some notes that Bernhard just gave. You know, if you go back 10, 15, 20 years ago, the approach we would take to international partnerships would be, you do this, I'll do this. We try to figure out how to make it work together. It's all internal to government. We've seen an explosion, especially over the last several years, of industry and commercial involvement. And so I look at, you know, a pilot plant that goes on here in several different ways. One is the open architecture. How do we make sure that whatever we do can work together? That we don't have the English plugs and the European plugs and the US plugs, different voltages, whatever the case may be. I think the other thing it does is, whatever we do, any positive demonstration to some extent lifts everything up. It shows it's viable, and it allows for greater investment and whatnot. And I think all those things are important. Our jobs now, to some extent, especially mine, is, you know, how do we enable industry? And industry is becoming, I mean, there's some of the teams that were shown here are multi-country, and so I can see that aspect being very important. And as we saw a lot today, different technologies arrive at different times. There's not one gas company, there's not one oil company, so if we're more advanced on one thing and you're more advanced in another, as long as we have these interfaces, as long as we have these kind of open architectures, hey, maybe if we fly a pilot plant and we don't have a certain piece of hardware, or you want to test out something, because I don't see one piece of hardware showing up. We know from a reliability point of view, we know from a redundancy point of view, we're going to want to have multiple things. We're going to want to grow our capabilities. So just like we have dissimilar redundancy in launch vehicles and life support systems, these processes are going to most likely evolve and grow along those lines. So I look at international partnerships, I look at the commercial multinational commercialization as being enablers to make all this happen.
Thank you. John, as Jerry posed, there are several technologies being developed, several aspects that will, in the future, need scale up, and you lead the consortium that's working on the ISRU demonstration payload study. So from your perspective, what are the challenges, and not just technical, but also programmatic, moving forward? Because as we all know, that these are just the initial work that we'll have to expand to the Lunar pilot plant, and the roadmap I presented showed several streams of work.
So firstly, brilliant points. Crucial to industry is having the pilot plant. We need to, in terms of the the design that we have in terms of our consortium going forward, it's kind of quite simple. It's relatively easy to design and should be relatively easy to build, but to test and to operate, it becomes very, very difficult. And to have some sort of pilot plant, to have these open architectures where we can find out what could possibly go wrong and try and do as much as possible end-to-end testing will help immensely. And for the Industrial Consortium and for the ESA Challenge project, we always had the commercialization in mind. And we always said, in anything we considered in the design, will it give us more oxygen? Are we sure it's going to give us more oxygen? And if we're not certain, then we go back to the pilot plant to see if that's true. And so the process we're using involves molten salt. We're constrained by the lander that we'd land on. We're looking at commercial landers. If we can get a commercial lander before EL3, then we go for a commercial lander. And we're constrained by the amount of power that can give us and how much oxygen we can deliver. But in terms of scaling up, we'd take exactly the same as will be done in ESRIC. That we'll start to get bigger and bigger crucibles, more and more oxygen, and eventually evolve a service on the moon to deliver oxygen. And using resources, and the main resource is power, is energy, and that will drive our scale. At the moment, we're limited by the smallest lander that we can accommodate on, but in the future, we will be scaling up to use large amounts of power to produce the oxygen we need.
Thank you. Now to Bertrand. We've discussed several technical points. You, as representative also of the consortium Mirror to Moon, which is very much in line with the sort of end-to-end demonstrator. What commercial opportunities and what commercial scenarios can you see in relation to a pilot plant, how to provide a service and how to integrate it in sort of the architecture of an end-to-end process?
Thanks for the opportunity to testimony. So first of all, I'd like to congratulate Luxembourg for pioneering this, let's say, space resources utilization topic. You've managed to create a community that is today convinced that moon settlement, but also SRU subject, is a key enabler of sustainability in space. And this for the benefit of international cooperation, as Jerry was saying, but also for the benefit of Earth industry. With regard to Euro to Moon, Melchiorre, we are not a consortium. We are a cross-sectoral association, non-profit association. That was created end 2021, so that's a very young initiative and that is to grow. Created by 4 members, Airbus Defence and Space, AirLiquide, iSpace, ESRIC, AirLiquide, I stated it, of course, and Jean-Jacques Dordain as honorary member. And the objective are 3. The first one is to create and to initiate a European ecosystem of complementary partners from space and non-space, but also public and private, to address the whole value chain of lunar resources. The second objective is to create a platform of exchange so that all together we could build up industrial roadmap to address the full value chain end-to-end. And the last objective, of course, is to motivate a European institution to invest more in that new sector to foster and accelerate the rise of the new cislunar economy. If I dare a comparison, at Air Liquide we've created something that is called Hydrogen Council in 2017. Today there are 130 members worldwide. And I can tell you that Hydrogen Council did a lot to foster massive adoption of hydrogen with regard to the preparation of a better future and energy transition. So let's do the same with space resources at European level. It's about creating a European Space Resources Council to be able to represent the full value chain and to close the capability gaps to arrive at the line altogether. Regarding the opportunity, there are many. To make short, I will just concentrate on the commercial one, and I have 5 of them in mind. First one would be propellant production and refueling. If you make a comparison, an airplane could be refueled up to 40,000 times, a car up to 750 times. A rocket upper stage and a satellite is just using once. And it's ending as a debris when it's running out of fuel. So clearly, the potential is huge. Huge for business, but also huge for sustainability. So if we manage to produce oxygen and in a second stage hydrogen on the moon soil, taking advantage of the low lunar gravity, we could organize some propellant depot on the moon surface, but also on different orbits, and then refuel the spacecraft, and consequently to extend their lifetime, consequently to reduce the cost of the mission, consequently to reduce the debris. That would be a super winning, let's say, commercial scenario. The good news here is that there is a lot of synergy and spin-in, spin-off opportunity with what's happening on Earth related to clean mobility using hydrogen and biogas for cars, trucks, but also tomorrow civil aviation. When you're speaking about clean hydrogen aviation, finally in-orbit refueling is quite close in terms of competencies and technology and ConOps. The second commercial opportunity would be about high power energy production and storage. And here again, hydrogen that could be produced from the moon is a perfect carrier to store intermittent energy. And again, here, this would serve the purpose of lunar night survival, it could serve the purpose of mobility on the celestial bodies, and it could serve the purpose on electricity provision for any operation on the moon. Again, good news, many spin-in, spin-off opportunity with what's happening on Earth with regard to energy transition, because we're speaking about electrolysis, fuel cells, liquefaction, storage. All this technology will be necessary on both sides, Earth and Moon. Third commercial opportunity, life support. We need oxygen, water for manned flight and habitat. Fourth opportunity, infrastructure and building using regolith and metals. And of course, the fifth one in itself, upscaling the production at industrial level of oxygen, water, hydrogen, regolith, metals on the moon. It's an opportunity in itself for many industries on Earth. As a conclusion, I would say that all this, of course, does not exist today and will rely on a very complex value chain to be implemented and new business model to be invented. And this can only happen through collaboration, as Jerry was saying. Collaboration between nations, between institutions, between space and non-space industry. And here I'd like to give 5 suggestions, maybe for institutions, to enable industry to help us to step into that endeavor. The first one is we need a common and ambitious vision for sustainability in space at 2040 at European level, political level, governmental level. This would allow industry and venture capital to invest in the subject, in competencies, in technology. The second suggestion is about breaking the silo between space and non-space. Today it's too, let's say, separated. There is two interests of doing that. First one is to leverage on the best Earth technology existing that could be spinning for the moon through PPP. And the second one is to make synergy in between ESA and European Commission on the budgets, because we are speaking about transversal things for space, but also for energy transition. The third suggestion is about techno-maturation. Today we are doing techno-maturation vertically, brick per brick or system per system. Tomorrow we have to be on the line all at the same time. So we have to do transversal maturation with end-to-end value chain. This would foster interoperability and the creation of consortia working in synchronized way. And two last things, demonstration, early demonstrations on subscale, low TRL, without fearing of, let's say, failing. No problem of failing, we have to try. We have to fly on every single lander and rover that is going to the moon and foster collaboration between Europe and the US for that. And last one is about export regulation. I think it's important that you hear that. There is a problem with ITAR regulation that is clearly preventing the collaboration between European and US industry on this topic of the moon. Today, each technology development that is on the moon falls in the ITAR regulation. I can tell you that Earth industry will never take the risk of ITAR contaminating its technology for this business until there is not, let's say, a huge vision and ambitious vision in 2040. So thanks for your attention. Sorry for being long, but very passionate subject.
Thank you. Apologies for misrepresenting the Euro to Moon group, and thank you for the very bold points that you put forward. I see that George has joined us. Hi, George. I would like to go back to what Bertrand was saying about the entire value chain, and as representative of the expert team at ESA and also the chair of the ISRU, technology work group at ISECG. What is your opinion of what does the pilot plant represent in the context of the whole value chain as tackled by ISECG?
Yeah, hello, good afternoon. I was told that there is interference coming from my mic, my input. Could you remove that and confirm you can hear me well?
Yes, we can hear you well.
Okay, so thank you for the invitation. I'm humbled to be part of this roundtable and for the opportunity. Apologies not being able to be there in person due to other overlapping commitments. Okay, indeed,
I think we have...
ESA has already defined its ISRU technology roadmap. Okay, does it work?
Yeah. Yeah.
Okay, I was saying that indeed the pilot plant is something that we already have defined part of the ESA Space Resource Strategy in 2019, as well as the ESA ISRU technology roadmap in 2020. In this roadmap, we define a value chain for ISRU that includes the following steps of prospecting of the resources, establishment in the rich areas of these resources, mining or excavation of the resources, followed by transportation of these materials to the plant itself, in this case, refinement, beneficiation, that could be physical or chemical beneficiation of these resources, and then followed by the production or extraction of the useful products for storage and further supply. In this value chain, the ISRU pilot plant indeed overlaps in most of these steps, because the pilot plant requires an excavator rover, which will then be addressing the step of mining or excavation, as well as transportation of the resources to the plant itself, where the following steps of refinement, beneficiation, production, extraction, and storage can all be addressed within the plant itself. So certainly the pilot plant addresses the value chain steps of ISRU. Also within the ESA ISRU delivery plan, one of the objectives is to define the architecture, the system and the operational concepts of a high-level development plan for a lunar pilot plant that can be compatible with Artemis mission scenarios. So this is an important step to acknowledge. ISRU is not only having its own strategy where a pilot plant is included. By the way, this strategy was issued in 2019, but there is also work ongoing to update or to refresh this strategy in the next few years, following our ministerial meeting at the end of the year at ESA. But we can also say already that ISRU is part of the ESA Exploration Terra Nova strategy roadmap. So we see ISRU as an enabler for Moon and Mars sustainable exploration. Then going forward towards the last part of the question, the technology working group at ESA and the expert team that I represent as a technology engineer here, we have a technology network working group at ESA composed by experts in different areas, where we address the potential technology development recommendations in different technology programs, in various technology programs. And ISRU is a technology area for exploration. We can address two types of developments, being research or technology push developments, or as mission pool requirements that come from system studies, where these requirements will be defined for either payloads or for missions, but they are specific for that application. And from that, we can also define technology developments. For the pilot plant in concrete, we have already planned in the fall of this year a pilot plant phase 0, so a mission architecture and definition study in the internal ESA concurrent design facility, from which we will derive the technology requirements for further implementation. And the pilot plant itself is going to be part of the E3P program proposal for next period. So we are considering that. And if accepted, there could be also the possibility to mature the lunar pilot plant concept further in industrial pre-phase A. So talking about mission definition, system definition, and pre-feasibility, together with technology developments up to TRL5 for that application. In parallel, there will be ground research ongoing for a terrestrial pilot plant. So these areas will all be addressing the technological needs for the pilot plant itself. And now to the question of the ISECG. So we all know that ISECG has defined a global exploration roadmap back in 2018 for the different destinations, LEO, Moon, and Mars for exploration. And in 2020 has defined a supplement for lunar surface architecture. Within this ISECG working group, there are several others. One of them is the architecture working group that defines architecture or system elements for that roadmap, and the pilot plant is one of them. So being one of them, another working group that I am representing for ESA is a technology working group, has the responsibility to define critical technology portfolio for that roadmap or for that architecture defined, as well as mapping these technologies into the applicability for the architecture needs and the exploration roadmap needs. We also go in depth when we have to assess gap assessments in fact for specific technologies for those architectures. And I had the pleasure, together with the other colleague present in the table, Jerry Sanders, to lead an ISRU gap assessment team for the ISECG. It was a very exciting exercise that we have done for two years approximately during the pandemic time, where we led actually an incredibly motivated group of professionals coming from 11 space agencies, if I remember correctly, 4 governmental groups, and in total more than 30 professionals working together for defining such a exciting technology area of ISRU. We have defined strategic knowledge gaps, we have defined the resources, each product and the applications for those products, as well as a work breakdown structure for consumables, for in-situ manufacturing, in-situ construction, technology simulants, analog simulants, technology capabilities and facilities capabilities. So I was very pleased to see on the first day that our very own Kathyrn Hadler from ESRIC has used the functional flowchart that we have defined at the ISECG ISRU gap assessment team. So I was really happy to see the product living on and being used by others. This was also the purpose that we have done such a report, an extensive report of 125 pages that others can be laying upon and build their developments. So part of that output as well were the planned missions, and it is recorded in the report that both NASA and ESA are planning pilot plant developments for lunar surface applications. So lastly, I wanted to say that we will take those outputs of that assessment in the report to flow down agency-related pilot plant critical technologies to a mapping platform that we have for the architecture and for the roadmap needs. And we are even discussing right now what can we do as a further gap assessment. Perhaps in the area of dust mitigation, we can look at in-situ construction for landing pads to address the detrimental effects of landing engine plume surface interactions. So I think this wraps up the question that was posed, and indeed that it's an international, interagency and inter-organization effort that we see moving forward, and we can judge by the success of this event once more that we all need to cooperate and collaborate, and we all need the support of each other to move this topic forward. So thank you very much for the time, and hopefully continue the discussion on the roundtable.
Mel, I'm just curious, who knows what ISECG stands for? Because you mentioned it a couple of times. Can you raise your hand? Have you ever heard ISECG before?
Okay.
Okay, so maybe somebody needs to explain what ISECG means. So, Jerry, what is ISECG?
So, ISECG, International Space Exploration Coordination Working Group. A large number of the space agencies, I can't remember how many in the end, meet and discuss how best to collaborate. Sometimes they'll pull together architectures, and so if you go to the website, you'll see the global exploration roadmaps that have come out. It's a way for all the government space agencies to understand what each are doing, understand where they're working on, because as Bernhard said, even with my budget, which is larger than others, ISRU, cryogenic fluid management, propulsion systems, there is just so much that needs to be done. No one nation, no one company can do all of these things. And so the ISECG provides an opportunity for countries, especially smaller space agencies, to basically say, look, with my budget, how can I really play an important role? And what are the gaps? And it's just one mechanism, but it's an important mechanism.
Thank you, Jerry. Thank you, George. Thank you for the extensive intervention. Kathyrn, thank you for having us in your sites, because at the end of the day, this is very much Luxembourg and ESRIC driven. I would like to go back to the terrestrial pilot plant, as mentioned by George, Jerry, and Bernhard. And as Bernhard said, the plan is to place the pilot plant here, an open source pilot plant where people can come and collaborate. What is the role that you see the pilot plant playing, and what is your vision of ESRIC working with the pilot plant?
Thanks, Mel. Well, the terrestrial pilot plant, I think, is absolutely critical. It's a critical facility for Europe. It's a critical facility for ESRIC. And what's wonderful about it, we hear a lot about the pillars, the 4 pillars of ESRIC. And actually, it's the one thing that ticks all the boxes for the pillars of ESRIC. So it's for the community, so we can actually foster collaboration through the community. It will enable research, both within ESRIC, collaboration with other partners, and it will support business to develop their ideas. And out of that, we generate new knowledge. We identify new gaps. Jerry and I have discussed at length about all the potential gaps that can come out from doing pilot plant trials. So I think it very much is at the core of what ESRIC is about. It's about generating new knowledge, but also providing facilities to enable the community to progress. And it's such an enormous challenge to put together lots of different pieces of equipment and make them work under challenging conditions, that we need this kind of facility. But also to talk about scale-up, I think scale-up is an issue that is, Mel, as you know very well, is a real challenge. We don't just scale our rate constants linearly. There's all sorts of factors that need to be taken into account. And so I think it will allow us to understand better what is missing in terms of our knowledge of scale-up parameters.
Thank you very much. Thank you to all of my guests, and thank you all for listening in. I don't know schedule-wise if we have any time for questions. Okay, so if there is any question for the panel. I don't have visual on the questioning on the chat, so I would need a bit of help on this.
Have we any questions from the audience? Everyone's very tired.
Stunned silence, yes. We've answered all the questions.
If you could introduce yourself as well.
Okay. Hi, my name is Dorian, and my question is related to some of the differences in environmental conditions that we might encounter on the moon versus ground tests here on Earth. So low pressure, low atmosphere, low gravity. So how hard is it going to be to adapt the results from ground tests here to application on the moon?
Yeah, let me just start. I mean, we will simulate the environment, not the gravity part, that's a bit difficult, but we also plan to build a large dusty vacuum chamber so that part of the pilot plant operation can actually be conducted in the vacuum chamber. So we're trying to make it representative. What we cannot simulate here is the partial gravity, other than if you have a nice idea, Kathyrn. But I think otherwise we try our best to do representative. That was one of the ideas, that we connect the big, large, dusty vacuum chamber together with a pilot plant, both located here in Luxembourg.
I think to go a little bit farther on that, it is something that we are all trying to understand, because there is not one facility that can do everything. So we can fly low-gravity spacecraft or planes for a period of time to understand the microgravity aspects. We can put things in dirty vacuum chambers, but depending on how much liquid nitrogen and time and effort you want to spend, it gets expensive every day you're operating that. We're talking for our pilot plant, for example, we would want to operate on the moon probably a minimum of at least a year. So when it comes to testing on Earth, how much can you do in a vacuum chamber? How much can you do in a laboratory? How much can you do in an analog site, demonstrating all those pieces? It's going to be a combination of things, and in the end, you're not going to be fully evaluating the moon. So that's why we take the leap and start putting hardware actually on the moon to get all of that simultaneously.
And if I can add, we had the presentation from David Beans and Thales. The ISRU DM payload study should definitely address that kind of question that you pose, because that would be the ultimate proof in the pudding, if you wish.
So if I may say, yeah, just quickly, the testing is really, really difficult. The dusty vacuum chamber, dusty vacuum chambers, space vacuum chambers are immensely clean. And if you walk up and say, can I do some testing in your vacuum chamber? I've got some of this ultrafine regolith, plus also I want to melt salt in it. Many people run away. So again, having that facility available is a big, big deal. And I say, we're working with our partners, and it was ABS who presented on Tuesday, and Metallisys and the Open University and Redwire, to try and de-risk all of that technology, trying to get as relevant environment as we can, and it may be the case that we'll have to do 1/6 gravity flights. Who knows? But it's the having hot elements with a material that's difficult to handle. That's the regolith, or we'll be using simulant in a vacuum chamber. Those three together are exciting.
Okay. I see that we have more questions.
We do. So we have a question from Clive Neal online, and his
Oh no, not Clive.
Hi, Clive.
His question for the panel is, not just for you, if the pilot plant is to liberate oxygen and metals from regolith, it can be sent anywhere on the moon, but where would you send it if it is to liberate water ice from the poles? Don't we need more data before we can send an expensive pilot plant to this and properly quantify the lunar resource value chain?
So I can respond for the oxygen and metal. Yes, the molten salt electrolysis is quite agnostic to the sort of regolith that is used. Of course, a lot of work is going on to define better and more accurately what the process parameters are. For the ice part, I guess that's on Jerry's part. So.
Well, first of all, I would say the pilot plant is notional, and I don't expect that there will be one, to be honest. Our planning is we have a pilot plant, we go to full-scale production. Whether it's water, oxygen, metals, I eventually see that as we go from the basic technologies, before we can commercialize it, we're probably going to have to show it at a scale that a company can get investment on. So I think you hit the nail on the head, Clive. To begin with, at least NASA's plans are to go to the South Pole. So we're looking more at the Highland regolith types of materials, what processes would be used for oxygen and metal extraction, and oh, by the way, can we find a Goldilocks location where there just happens to be a permanently shadowed region that might have water that we could eventually mine it. So we may have a completely different pilot plant for that water mining. If we want to get pure aluminum or some other metal, the processes that we've talked about today don't give us that purity. So if we do molten salt, if we do molten regolith electrolysis or carbothermal, we get our oxygen, but we don't get a pure metal per se. So there's probably going to be a follow-on to some extent. So, the short answer is what you are particularly trying to accomplish with your pilot plant, that will set some levels of requirements or specifications, and as Bernhard said, that's one of the first steps that we really need to do.
If I may follow on that, I think
George.
it also, yeah, thank you. I think it also has somehow much to do with the specific capabilities on each potential partner. As we have seen during the ISRU gap assessment team, we have a worldwide agency capability for different technologies. And we have seen that for regulated processing, many potential partners have different capabilities. ESA, for example, is focused on oxygen extraction from regolith and metals extraction also from regolith. But we also know that other partners, in premise NASA, has power capabilities that enables them to go in permanently shadowed regions, enables them to operate in those regions without sun illumination. And perhaps they are also looking into that area of extraction more in detail. So at the end, I think there is space, as Jerry said, for more than one pilot plant. I'm talking about from the technical point of view. And in the end, if we are to do this collaboratively and cooperatively, then there should be also space to address a different type of technologies. And we will have to decide, of course, what is the location for the human landing, where we could provide those consumables useful for the crew.
Thank you. And I guess to go back to Jerry's point very briefly before we move on to the next question, if we would want to produce certain pure metals, then yes, we would have to have a lot more information also on the concentration and the availability. And I'm looking at Kathyrn here for the reserves where to actually pick up that kind of materials for processing. Next question.
Which is related.
So I think the community is asking also how they can join this definition of the requirement for the pilot plan. You talked about open architecture. So how concretely the community can help you defining the requirement for the ground pilot plan?
That's a good question.
Yep. I
Bernhard?
think I thought about it just today, so I still have to make the plan for how we're doing it. But basically, I think we will start with a workshop to gradually start collecting ideas for requirements. That will be an open workshop. But my idea is to put something online, really on the internet, an open discussion forum on providing feedback on the requirements. So I still need some advice how we can do that. I'm also looking for your advice. But I would really dream of having an open discussion forum on those requirements, make it really a community product, and present maybe a draft version in 1 year from now to this community, maybe organize some splinter session in this context. We still have some time. We will start an industrial activity, what we call the phase AB1, to define requirements that will run in parallel. But my goal would be that in 1 year we have mature requirements we can discuss at this very conference next year. And any ideas you have how we can do that in a way which is really engaging would be very welcome.
Yeah.
Thank you. Next question.
I'd like to, again, off the top of my head, you said something really important as well as what Kathyrn said. So on the ground, we're looking at building a pilot plant here in ESRIC with the idea that as long as you have understanding of interfaces and modularity, you could potentially swap things out. And so it's an evolving pilot plant. A new technology comes in. To some extent, you can kind of think about that as a possibility for the moon, that we have a modular power plant or pilot plant. And so, for example, say there's a molten salt electrolysis unit. The tailings that come off of that, somebody in the future could bring up a module specifically designed to work on those tailings to get the next thing. So we could start envisioning almost as a way of helping industry, this instead of having to fly a completely new pilot plant at another location, if certain technologies have proven to be just, I don't need to work on that more. AirLiquide comes forward with a liquefaction and storage tank for oxygen. Do I really need to build a whole new technology? Maybe, maybe not. But we could start looking at other things. And so when we talk about this pilot plant, that's something that we might throw on the table as well.
Yep. Absolutely. Thank you. So next question.
So the next question is a bit of a follow-up of Dr. Maurice's questions. How do you address the open source access and data and to the testing as well?
That will need to be something that we need to think carefully. Of course, depending on how this is done and what kind of collaboration can be established, for example, with NASA, of course, that will much depend on how we procure this activity, because, of course, ESA is participating in a strategic partnership with ESRIC. However, we have to make sure that the data produced is of service for the member states, first and foremost, and then it will come down to the sort of agreement and partnership that can be established with other entities like NASA, like JAXA, and whoever would like to participate. Of course, being European funding, the member states of ESA would have access to that kind of data.
Yeah, one more question. This is Carlos from iSpace. It's a similar question.
You might need to stand up.
There you go. Sorry.
Yeah.
Sorry. Yes, a similar question. So how can we, it's a great idea, the pilot plant, fully supportive on that. But how can we, industry, concretely support, not only in using the pilot plant, but in designing the pilot plant? Because the definition of pilot plant is like a step before going to full production, and in a way, we industry need to be involved. So how can we industry be concretely be involved in the design of the pilot plant and the use of the pilot plant?
Well, I think there are different steps. Firstly, we need to be clear about the requirements. And the pilot plant is just the name. Pilot plant is an architecture, there are different elements, post-processing, pre-processing, and so forth. So I think, firstly, we need to start defining the requirements and scope it, what does it really mean. It needs to fit in a building somewhere, so we can also not be too ambitious. I think ESA will not fund the development of a full pilot plant. We will fund elements of it. We need to be clear about interface requirements, and then we want to invite industry to provide and plug-and-play modules. So I think for me it's actually more important at the early stage to define the whole architecture, the modules, define ICDs, the interfaces, and be clear what ESA will develop and what we expect others to provide, commercial partners, industry, academia, or the international partner. And this step of formulation is what we want to do this year, next year. And in this formulation step, we really would like to engage the community in a practical way. And we still need to find the best way of doing it, but that's the intent.
Mm-hmm. And to complement what Bernhard said, this wouldn't be the first time that ESA has done something like this. I mean, we can cite Melissa, which is basically something very similar, and it's one of the many similarities of ISRU with things like support for astronauts and plants where you have an evolving nature of what it is, and you discover new technologies, new synergies, and new things. So, as Bernhard said, here we need to define what the requirements are, what is the backbone that will represent the fundamental elements, and where industry can come and test their theories, their practice, and their ideas in general.
But maybe if I can add on that, and that's a suggestion to step onto the question of Carlos. There is a collaborative exercise to be organized between space agencies and industry to size the demand based on the future commercial usage. So I think we could estimate what will come first. And then after, there is a big, let's say, question and answer exercise to organize transparently, because we are speaking about a universal endeavor. So that without displaying all the strategy of each company, each one could eventually contribute, saying, okay, I will need that amount of, I don't know, propellant. My propellant will be this one. I will need that amount of energy and power. Because sizing of the need over time will be key to define the right technology from the beginning. Yeah. Because it might be different solutions actually. We could start by a pilot plant with a very minor demand, and finally just discover that the demand would be huge and the technology could be different. I say that because we have this topic on Earth, huh? So.
Sorry, George, you go.
Excuse me, Mel. This is absolutely true, Bertrand. In fact, Bernhard already mentioned it briefly, which is we will also in parallel define a lunar pilot plant, and we will flow down the requirements for the space system into what are the needs that you are mentioning for the terrestrial plant. So we need to know exactly what you said. We need to know what are the operational needs for the lunar pilot plant, and we already will have to define the interfaces between the different subsystems of the lunar pilot plant, and this will be flown down as well via the workshop that Bernhard mentioned or via other mechanisms, but it should be flowing down from the lunar pilot plant operational needs into the pilot plant on Earth, on the terrestrial research facility. And then if the interfaces are defined, if the operational need is defined, then indeed trade-offs of different technologies and systems can be done in the research facility to find the optimal solution.
We have one more.
Thanks. Thanks, Carlos. Hi. Sorry, I sneaked in, I guess. I don't know. I was given the mic. I'll be very quick.
Voice saying no more, but
It'll be very
Juliet's
quick.
the lady in charge. It's up to you, Juliet. If they have very quick answers. Yeah.
Yes. Thank you very much, Juliet. So, Antonino, I'm a space lawyer from the University of Luxembourg. Someone previously mentioned compatibility with Artemis. So my question is, how does this fit with the Artemis program? And especially because ESA hasn't joined the Artemis Accords, maybe it shouldn't even do that to a certain extent because it's not needed. But wondering how this integrates into the Artemis bigger picture, both from a program perspective and also legally from the political commitments of the Artemis Accords as well.
Don't look at me.
Well, okay, it fits. Let's close it.
It fits. Yeah, the Artemis Accords, obviously, we had a whole panel and workshop on the legalistic aspects. That obviously needs to continue to work. One of the things that came up that I think we really need to spend more time on is this was a really good workshop on the supply side. We talked a lot about different technologies for making propellants, for constructing things. A really important point is, what are we going to use that stuff for? So to some extent, we do need to spend more time on the demand side. And so what ESA has done, what NASA has done is, within our plans, we are purposely pushing forward technologies for being able to make these things with a semi-nebulous idea that there will be a customer downstream. And so, you know, if we build it, they will come kind of an approach, which is good to start with. And at the technology level that we're now, that's fine. Because no customer is going to sign up for getting oxygen until we do the ground development of the pilot plant. But that is the goal, and so we really do need to spend more time and maybe have workshops on, if this amount of oxygen or water existed, give business cases to companies for what would you do with that? If you were able to build a habitat, what would you use it for? And that, I think, would spur new ideas on what Artemis should be or what Europe should be doing. So that's just hopefully a quick answer.
Maybe a very quick add-on, Thierry. Supply and demand match is key. Working on business plan, so on vision is key to engage stakeholders and shareholders of big industry. So clearly I can tell you that each time we come with an investment proposal, the question is, where is the business plan? So clearly, we need to work on that demand aspect.
Yeah, NASA and the Applied Physics Lab had a half-day workshop called the Supply-Demand Workshop. Look it up online. Much more than a half day is needed.
And the last one, that's for ESA and NASA, and related to the question on Artemis Accords. I think we need to take some time to see if we could simplify or eventually waive that ITAR application on the moon subjects, because clearly, and that's preventing a
Well,
lot
ITAR
of
is a
collaboration.
completely different thing.
I know,
and way above my pay grade from a NASA perspective, but.
Okay, thank you very much. Thank you all for your questions. Thank you again for my guest and for George's participation online. I now pass it on to Lisa.
Thank you so much, and thank you to all the panel. Thank you very much, but Kathyrn can remain.
Thank you.
Oh.
Come on.
Thank you very much.